So this is just to summarize what we have seen so far for stationary Gaussian processes. I've sort of summarized the results here. So you have a complex Gaussian process. The real and imaginary parts are independent at any instant t, and they are also Gaussian with a zero mean and equal variance. Then this is the amplitude. Amplitude is Rayleigh, and the phase is uniform. And except now we look at another time instance, so you have another amplitude. This is Rayleigh. But what we are interested in is the joint distribution between RT and RT plus tau. So if I define R of t to be R1 and R of t plus tau to be R2, we want the joint distribution and also the correlation. We already, in the previously we have just shown that the joint density function is given by this expression. Notice that quickly you have you have R1, R2 term, then the exponential terms, and also this I naught, the Bessel function term. I naught of x, by the way, is integral 1 over 1 cycle, 1 over 2 pi 0 to 2 pi, or the cosine will, it's just the equally, or it being symmetric, it's also, you can do it over half cycle, 0 to pi e raised to x cos theta d theta. If you make a slight change of variable, you can write it in terms of sine theta over an even region. And then you expand it as e raised to expand it as e raised to k over k factorial. But then notice that all the odd order terms will vanish because sine 2 to the power odd order terms are over minus pi by 2 to plus by 2, 0. So only the even terms are maintained. That is 2 times 0 to pi by 2. But this is the integral of 0 to pi by 2 sine 2 and theta is well known. That's this expression. So if you substitute, it's a classic expression for I naught. I substitute that I naught here. If you want, you can also write down the joint density function in this manner. Now this is the expression we are going to use to find out the correlation between R1 and R2. So we substitute this density function here. We simplify this. So I expand the I naught term using the summation and separate it out as in terms of R1 squared and R2 squared. I call this whole quantity to be U, this to be V. So U is going to be, so we get for R1 squared is going to be U multiplied by 2 sigma squared 1 minus k squared. If you make the substitution, you will get two separable integrals. And this, of course, you can keep integrating by parts. You come up with this expression. So the interesting thing to notice, this is again this is the correlation between R1 and R2. So interesting part to notice is that there is a square here. Right? We had this expression before. I just want to go over one simplification, at least in show all the key steps. So notice that these two terms are identical. So the terms are identical. So you can write this squared, in fact. Now the interesting thing is this last term can be written in terms of hypergeometric series. So hypergeometric series of alpha, beta, colon, gamma, colon c is alpha, beta goes in the numerator. Alpha gets updated for n terms, alpha, alpha plus 1, etc. Same thing with beta, same thing for gamma in the denominator, Cn over n factorial. Now this is a classic, so this is the only relation I want to use. So this is a classic relation for hypergeometric that this also can be written in terms of this. So in terms of hypergeometric, this E R1, R2, So notice that k is a function of tau, of course. K is a function of tau. So this could be written as this, you see it as 3 by 2 plus 1, etc. up to n terms. So this will be n minus 1 here, n minus 1, and n minus 1. So notice that this is starting from 3. So if you want, we can write this as f of 3 by 2, comma 3 by 2, and here you have 1, 2, 3, etc. up to n. So that's going to be n. So this is going to be 1, and then k squared. K is a function of tau. That's this expression. You also have before that here, you have 2 sigma squared, 1 minus k squared, the whole squared f term. So we had 2 sigma squared, 1 minus k squared, the whole squared f of 3 by 2, comma 3 by 2. Now if you use this substitution, this can be written as f of, notice that gamma is here 1 minus 3 by 2. So this is minus half 1 k squared. And this, if I write it as a series, so this 1 minus k squared goes away because this is 1 minus k squared, 1 minus 3 by 2, minus 3 by 2. So 1 minus 3 minus 2 cancels with this. So you end up just having 2 sigma squared here. Now if I substitute for the hypergeometric term here, multiplied by, let's notice that there is a pi by 4 here. So when you multiply by the pi by 4, this in fact becomes pi by 2. So with this, if I substitute for the f term, this becomes pi by 2 sigma squared, summation n equal to 0 through infinity, minus half plus 1, etc., minus half plus n minus 1. This twice because of this, divided by n factorial k to the power 2n. Now notice that minus half plus half is half. So all the terms from here onwards is plus, except the minus half term. So I could write this as pi by 2 sigma squared, summation n equal to 0 through infinity, minus half first term, then half, then 3 by 2, etc. Last term is 2n minus 3 over 2. This whole thing twice, so squared over n factorial k to the power 2n. If you want, we can the same thing. We could also write this as notice that you have here 1, 3. For the next term will be 5 by 2, etc. So you have 1, 3, 5, etc. in the numerator up to 2n minus 3. And in the denominator, you have, if you take this, so you have here 2, then you take 2 into 2 you have 2 multiplied by 2. N factorial is of course 1, 2, 3, etc. So 2 into 2, then 2 into 3. So this is 2 multiplied by 3, etc. up to 2 multiplied by n. That also comes twice, so we can write it like this. And I'm going to add one term extra here, so this twice. So this is now going to read this way. There is a summation n equal to 0 through infinity of pi sigma squared over 2. Now this, if you want, you can expand this as pi sigma squared over 2. And if you just put n equal to 0, you get 1. Then the next term will be half squared k squared over 1. The next term will be 1 multiplied by 3 multiplied by 2 multiplied by 4 squared k4 over 3 squared, etc. In other words, the general term is of this form. Now I'm going to write, the interesting thing is I'm going to write this series in terms of the two elliptic integrals. And that's where we will, I showed the results earlier, but a bit more details. So if the two elliptic integrals are, the elliptic integral of the first kind is integral 0 to pi by 2, 1 over square root of 1 minus k squared sine squared theta d theta. And this is this one in fact comes up in the pendulum, the swing of the pendulum. So the question is, how do you simplify this? Expand this as a binomial series and simply integrate it term by term. So I'm just going to sketch a couple of steps here. So this can be written as summation n equal to 0 through infinity, integral from 0 to pi by 2. If you expand it, minus half minus 1, etc. up to minus half minus n plus 1 over n factorial minus k squared sine squared theta to the power n. And there is an integral d theta. So if you, so remember that my integral 0 to pi by 2 sine squared n theta d theta it gets solved only for when n is even. And then if you substitute those results, this can be written as summation n equal to 0 through infinity 135 up to 2n minus 1 over 2n over n factorial. That's from here. Because you have minus 1 to the power n, minus 1 to the power n, so the minus cancels off. Then you have k to the power 2n. Then integral 0 to pi by 2 sine 2n by theta is 135, again 2n minus 1 over 2n n factorial multiplied by pi by 2. So if you put that up together, this is now going to read pi by 2 multiplied by summation n equal to 0 through infinity one, 3, 5, etc. 2n minus 1 over 2, 4, 6, etc. up to 2n the whole squared k to the power 2n. So this is for the elliptic integral of the first kind. And similarly, if you look at the elliptic integral of the second kind, so that's going to be integral 0 to pi by 2 square root of 1 minus k squared sine squared theta d theta. Go through the exactly the same expansion. For example, this will be n equal to 0 through infinity minus half plus 1 etc. minus half plus n minus 1 over n factorial. Then you have minus k squared sine squared theta to the power n d theta. Integral 0 to pi by 2. So this, if I pull this out, n equal to 0 to pi by 2, you have, I need to write 1 minus half, then, so this is minus half, this is going to be 3 by, this is going to be half, right? Minus half plus 1 is half. The next step is going to be 3 by 2, etc. Uh, 2n, you can see from here, 2n minus 2, 2n minus 3 there. And from the sign you get and here you have 2, 4, 6, etc. up to 2n. And you also have, you have to take care of the other terms, half, half plus 1. In other words, when you do the sine to the power 2n theta, you get 1, 3, 5, etc. 2n minus 1 over 2, 4, 6, etc. up to 2n, and pi by 2, and there is also a k to the power 2n. So the bottom line is, if you put this together, this now reads pi by 2 multiplied by 1 minus n equal to 1 through infinity, 1, 3, 5, etc., 2n minus 1, 2, 4, 6 up to 2n, the whole thing squared, k to the power 2n over 2n minus 1. So the important thing is to notice this minus sign. That's because, as I explained here, there is only one place the minus is going to come. So the minus sign will be there. And so what we have to look at this is now simply look at 2ek squared minus 1 minus k squared. This is the Uhlenbeck result. So we can substitute this summation here. We can substitute the a K series into here, and if you simplify, you're going to get that step. So that's the final thing I want to show. So notice that for the elliptic integral of the second kind, this whole expression is going to come here. And elliptic integral of the first kind, we are going to take this expression and plug it in here. Then I'm going to show that what we get is this term, which would be the correlation between the two random variables. So let me so 2ek, so I'll start from here. 2ek squared minus 1 minus k squared kk squared is pi by 2 So this now simplifies as pi by 2. 2 minus 1 is 1. So right now it's only a matter of putting the terms together. Then this is going to be minus 2 over 2n minus 1 plus 1, 2n over 2n minus 1, the whole squared. But this is going to simplify as minus of 2n plus 1, right, over 2n minus 1 plus 2n squared over 2n minus 1 squared, and this thing is, you can see here, so minus 4 n squared minus 1 in the numerator plus 4n squared over 2n minus 1 the whole squared, so that which turns out to be 1 over 2n minus 1 the whole squared. So in other words, this now reached pi by 2 multiplied by 1 plus summation n equal to 1 through infinity, 1, 3, 5 up to 2n minus 1, 2, 4, 6 up to 2n, the whole squared, k squared tau over 2n minus 1, the whole squared from here. And if you look at that, that's exactly this expression. Pi by 2 sigma squared 135 2n minus right. So 135 up to 2n minus 1, the whole squared, there is a whole squared there, to right, so if you want this also we can write as pi by 2 sigma squared summation n equal to 0 through infinity 135 up to 2n minus 1 246 up to 2n the whole squared over k squared tau over 2n minus 1 the whole squared. Same expression as this. That's exactly this expression, except I forgot to bring up this square here. So consequently we get this thing to be so this is going to be, so you have a sigma squared there, so this is E R1 R2 over sigma squared, or E R1 R2 is, so we get this expression, this multiplied by sigma squared is equal to E R1 R2. So here is the summary. If you start with the two, if you take two time instants from a jointly Gaussian process, each of the amplitudes are Rayleigh, but their joint density function is given by this expression, and their correlation coefficients can be expressed either as an infinite power series or in terms of the elliptic integrals of the first and second kind, and this result is due to Uhlenbeck and goes back to I think about 1948 or so. Uhlenbeck is I think he worked in the Manhattan Project, and after that was over, I think he must have started working on this integral.